Thank you very much for the introductions. So as the final talk, I would like you to relax and I will give you a nice story of physics. The point of this presentation is to give you an overview of advanced concepts aiming at very high efficiencies. And it's really intended, let's say, as a speaking guide. The idea is not to make you fluent into new concepts, but it's to make sure that if you get to talk with colleagues or friends or people you might meet working on these things, you would have an idea in which case to put them and to have some notions of what they're trying to do, okay? So what are these new concepts for PV conversion? Well, basically the idea is to try and aim at something, at anything that silicon would not do very well already. Now, you know, we mentioned how big data are necessary if you want to have foundings these days. You might want to set on some disruptive ideas as well. So basically, this can include quite many different things. You can aim for some things with different processes and claim it's some new concepts of processes. You can aim for specific mechanical or optical properties, or you can aim for something which will go towards much higher efficiencies. And now that's the part on which I will focus. And you see on this graph here the difference which you can get between the best module, the best cell, and the best theoretical efficiency for single junctions. So if you see this graph, what you read here is that there is not much margin here to win if you are staying within the single junction technology and you want to get cells to even higher limits. Now, why would you like to go towards even higher limits? This Jean-François has already mentioned before. You might want to decrease the cost, the levelized cost of electricity. You might want to aim for very, very specific applications where space is very limited. And I will not go into too much into details here because what I really want to focus on is physics. Now, of course, there is a question which often comes when you talk about these new concepts, and that is these new concepts, they have been around for 30 years. So how new are they, and why do you keep trying? And I would say that there are mostly three types of answers to this. The main one is to say that, of course, these ideas not necessarily aim at making it to market within 5 years, but they are addressing bottlenecks of current technologies. And if you don't address bottlenecks well in advance, well, at some point, you're going to be completely limited. And as basic research takes some time, you'd better start this as soon as possible. The second idea is that when you do these kind of things, you get ideas from basic PV science, and this can help for anything you'll do. And I hope that through this presentation, I will also be able to give you some physics insights which might help you for whatever technology you are currently working on. And the last idea is that when you do basic research, you know what you're looking for. You might not know what you're really going to get at the end of the day. And so doing this research can have many other type of applications, even besides PV physics. And I think it's important to keep this open perspective. So what I'm going to do with this presentation is really two things. Is to introduce this basic idea, which aim at overcoming the Suchet-Quasar limit. And I will try to show you that this is not just science fiction, it's actual science. And I will try and give you some experimental state-of-the-art results on these different concepts to see where we are. Now I will do this, of course, in 3 parts, as should be. I'll first go back to the Suchet-Quasar limit for just a few slides. We started with the Suchet-Quasar limit. I think it's only fair that we also end with it. And I'll try and give you 3 complementary approaches. One which you can use when you have dinner or beers with friends and you want to explain basic limitations of solar technologies. It actually works. And we'll go towards more sophisticated descriptions. The second idea is to present you the usual suspects which are considered when aiming at very high efficiencies. And the third point will be to try and step even further away from equilibrium and see how you can aim for even newer concepts than the one which I usually presented. So let me go back to the Suchet-Quasar limit. And the first approach I'd like to give, and there again, I'm really just here paraphrasing what Uwe already presented and Jean-François mentioned. The first one would be the hand-waving approach. So what happens when you try and convert solar energy into electricity? Well, essentially, you start with a material where you have few excited carriers and they're cold. Then you shoot light into this, you absorb photons which have more energy than the band gap. You create a very messy state here, which is non-thermal. You can't describe this state easily. You've got carriers all over the place. But then due to interaction, these carriers will relax And the question is, how many carriers do you have here? Well, essentially, you generate one carrier at max in this very simple picture for each photon above the band gap. So you integrate the solar spectrum above band gap. And this will give you how many carriers you have here, and so how many carriers you can dream and extract. Now, these carriers relax towards first a hot many carrier state, and then they will go towards an ambient temperature distribution, which is at the same temperature as this one, but now with much more carriers. And now when you do PV, what you do is that you extract electrons in the conduction band, you make them work through an electrical load, and then you plug them back into the valence band. When you do this, the energy you can dream and get for each of these electrons is essentially the band gap, which you read here very easily. You take an electron here, you put it back there. How much energy did the electron give you? The band gap. So the power, let's say the average energy per second which you can get would be here, the number of carriers which you generate times the band gap. Okay? And this, of course, tells you that if the band gap is very, very small, you're going to have zero power. If the band gap is very, very big, you're going to have zero power. There is an optimum somewhere in between. And these are the photons which are lost. This is the energy which is lost due to thermalization. This is the energy which is lost due to non-absorption. So this here is a very, very rough idea, but it already gives you the idea that you're going to have a maximum here somewhere. Now, why is this idea so rough? Why is it not satisfying? Why is this not already the Shock-Quasar limit? What's the difference between this picture and the Shock-Quasar picture? The main difference is, here I'm talking about the total energy which I'm getting from the electrons. But we're not interested in the total energy. What we're interested in is electrical power. Now, this slide here is about thermodynamics. And as Sasha mentioned yesterday, everybody hates thermodynamics. So I'm going to try and keep it short and yet try and give you the main idea behind this very basic PV thermodynamics. What you're really interested in, from an engineering perspective, is not the total energy times number of carriers, is the voltage times the number of carriers which you extract. Now, a way to write this is to say that for each electron which I take out from here and put back there, I have some work. This is what I'm interested in. This is the voltage. But I also have some heat which is given to it. Now, this would remind you your old nightmares from when you were undergrad students, because it's just the first law of thermodynamics. So if I take an electron here and I put it there, what is the work which I'm getting? Now, there is a very clear answer to this. And this answer stems in chemical potential. Chemical potential, you have one for electrons here, you have one for holes there, and just like temperature would give you, so let me rephrase this again. If you consider thermal states, states at equilibrium, easy states, they are entirely described by just two quantities, temperature and chemical potential. The temperature will give you, for instance, the average energy per particle. Temperature and chemical potential will give you the total number of particles. So with these two quantities, temperature and chemical potential, you can express everything. Okay? Now, you might remember that this chemical potential is also related to the notion of free energy, which Jean-François introduced before. Free energy is the maximum work you can get when you make a transformation. Well, that's precisely the quantity we're interested in the first place. So when you say that the chemical potential of electrons is this one, and you say that the chemical potential for holes is that one, what you're saying is that if you do the very simple transformation of taking one electron here and put it back there, the maximum work you can get is the difference between the chemical potentials of these two populations. So what I'm just saying here is that the maximum work I can get, which is at the end of the day the voltage, is nothing but the difference in chemical potentials. So I'm just reminding you here this very, very basic expression, and I'm reading it from a thermodynamic perspective. When you say that voltage is the difference between Fermi levels, what you're really saying is that these Fermi levels are the chemical potentials for these carriers. So now we can just go back to this expression here and consider that now the power which we're interested in is not the total power for the electron. It's just the power which is associated to work. It's the electrical power. So now what I'm considering is the number of carriers which I'm generating times the work provided by each of these carriers, that is to say the voltage, that is to say the Fermi level splitting. It's all the same story. Now, if I do this, what I'm saying is, inside this energy, which I'm extracting from the device, part of this energy is actually the work I'm interested in, and part of this energy is the heat, which I'm not interested in. So now, if I make this distinction, what you see here is that this is the heat, which I'm not interested in, and this is the electrical work, which I was interested in the first place. Okay? It also gives you some hand-waving perspective, which I think is interesting here. If you have more particles here, if you have more electrons in the conduction band, more electrons mean the Fermi level goes closer to the band. It means you have a larger Fermi level splitting. It means for each electron which you're getting out, you're going to have more work. So the more carriers you have, the more work you're going to have per carrier. Okay? Which means if you don't extract carriers, you have the maximum amount of carriers in the conduction band, you've got the maximum voltage. Now, if you start removing these carriers because you want to get this energy, you're not just satisfied with the carriers sitting there, you want actually to get them. So you start extracting the carriers, but now you have fewer carriers in there. If you have fewer carriers, chemical potential goes down, which means for each carriers which you extract, you're getting less and less energy. You're getting less and less work. So what I'm really telling you here is just the IV curve of a solar cell. If you don't extract carriers, you have a lot. Oops. Let me go back here. If you don't extract carriers, you have a lot of work per carrier. You've got max voltage. As you start extracting carriers, you've got less and less voltage up to the point where you don't have voltage anymore. That's just the IV curve, which you've been knowing for ages. But it's the IV curve from a thermodynamic perspective. Okay? So this picture tells you that you're going to have a trade-off between voltage and current, is that if you want to have maximum extracted power, you're going to have to work at maximum power point. Now, if you look at this graph here, which is now slightly more complicated, you might picture that there is something weird. Do you see it? It's not summing up to full power. There is here something which is missing, something which I have not included into the calculation yet. Do you know what it is? So far, what I've been telling is carriers are generated, they interact with each other to form thermal distribution, they relax towards steady state, okay? This is where I try to extract them, but is this really the end of the story? Not really. If I just let them here, let them be and wait forever, at some point they're going to relax towards the bottom of the band. So I need to include here the fact that I'm going to have some radiation. Now this, of course, is related to the photoluminescence talk which Laurent gave us the other day, and it's related to the generalized Planck law. So what you emit is related to the emissivity of the system times the Fermi level splitting, which is really the voltage. Okay? So I'll skip on how this thing is related to the absorptivity, but if I include this thing now, I will put it here to make it visible. This is this violet curve here would be the energy which is lost due to radiation. Okay? So now we have here all the basic transformation and loss terms which we might be interested in when we do photovoltaics. Now, what we are going to try and do with new concepts is to tackle these different loss terms. One way to do this, of course, is the way which Jean-François introduced with multi-junctions, so I'm not going to mention that one. All the more because it's already working, right? So what would be the fun? There is another way to overcome the Shockley-Quasar limit, which is also working today. And this idea is very simply concentration. Now, concentration seems easy. It actually turns out that it's slightly more complicated than it might seem in the first place when you really try and understand what is happening. So concentration is to say you have a sun which is facing a cell, and now I'm adding a lens on top of this. And then, for some reason, concentrating light makes so the solar cell works better. It means for the same amount of power reaching the cell, you're going to manage to get more work out of this. And when you say it that way, it is actually not obvious. And I would like to give you here two complementary ways of seeing what is happening. The first way, before I do this, I need to explain how to express concentration. And here, there is one specific trick which I think is really not often discussed, and I won't have time to go much into details, but I still wanted to put it here, and if you want to go into discussion, we can make this afterwards. This here is the black body radiation for the sun, which is received by the cell. I want to highlight this term here, this quantity, which is called the optical étendue. Usually, you see it written as the solid angle. And it is not. It is not the solid angle. It really is the optical étendue. Now, what is the difference? The solid angle is defined. So if I have the sun here, I've got the cell here. I say that the sun can be seen under a given angle. The solid angle would be the integral up to this angle of sine theta d theta d phi. Right? That's the usual expression which you know. Now, if I calculate this for the sun, what I'm going to get is something like 4 pi sine squared theta divided by 2. Okay? What you really should put here when you consider this, the black body radiation is not this quantity. It is the optical étendue, which is almost the same thing, except you have a cosine on top of this. Now, I can explain you where this cosine comes from, but there again, I'm a little bit short in time, so I'm going to skip it for discussion. If you want to know the details, I can explain it entirely. But the difference here is that this quantity here is not exactly that. It is pi times sine square theta. Now, if you work at low concentration, so this angle here is small, what I will call the concentration factor is the ratio between, sorry, I just put here for clarity, to be entirely rigorous, and I can discuss this afterwards. The concentration factor is the ratio between this quantity when you concentrate and this quantity under one sun. Okay? It is not equal to the ratio of solid angles. If you work at very, very low concentration, if theta here is small, then these two things are almost equal. Okay? If theta is small, this is almost equal to theta, so this is pi times theta squared, and this here would be 4 pi times theta squared divided by 4, which is the same thing. But if you work at high concentration, if you think that theta here is so big that the sun looks like almost like all the sky, theta would go to pi over 2, this guy would go to pi, while this guy here would go to 2 pi. Yeah, half a sphere is 2 pi solid angle. This is not breaking news. So at high concentration, what you get is almost half of the solid angle. Okay? So this is a little bit of detailed technicalities, but if you work with concentration, and you are much more likely to work with concentration than to work with new concepts in your labs, I really thought it was worth taking the 2 minutes to explain these things through. Okay? So, why is concentrating light helping conversion efficiency? I would like to give you here two perspectives, which of course give the same result at the end of the day. The first one is the local perspective. So I'm going to sit here just at the middle of the cell and see what happens. The second perspective is a global perspective. I'm going to consider the device as a whole and try and understand what is happening. Global perspective works like this. If I'm under one sun, the short circuit current which I can get here will depend on what comes from the sun and the optical étendue of the sun. I also have to take into account the fact that I'm giving out some radiation myself, and I'm emitting this inside the étendue of the cell, this time times the black body radiation of the cell. Okay? Now, when I do concentration, what is happening? Here, locally, when I'm at this point, I see the sun with a larger angle. So I increase this thing here by the factor C, which I defined before. For emission, I'm still emitting locally the same thing going in all directions, so this is unchanged. Now, the open circuit voltage which I can get is the log of this ratio, so now it increases with the log of concentration. Okay, and this you probably know from before. I can give the complementary picture. Now I can consider not just the local current density, but the global current produced by the cell. If I'm here, so the global current would be the current density times the surface of the cell, right? This, again, is not breaking news. The global dark current is the local dark current density times the surface of the cell. Okay, there again, this you knew from before. Now, this cell here has a given size, which is the same as the size of this lens. So I have just as many photons reaching the lens and then focusing onto the device as I had photon reaching the cell in the first place. So the total current which I'm getting is exactly the same, of course. Here, I've got as many photons reaching the device as here. This thing has been increased, but this thing has been decreased. So the total current is the same. But now, because this cell is smaller, the total dark current is decreased. So you can see concentration in two ways. You can say that concentration helps you increasing locally the current density. You can say that concentration helps you decrease the global dark current. And of course, if you do this calculation here, you get exactly the same increase in VOC, which makes sense. It should not depend on the perspective you take to change physical results at the end of the day. So what this here really tells you is that what matters if you want to increase VOC and ultimately the efficiency of the device is that you should reduce the mismatch between the angles towards which you see the sun and the angles towards which you are actually emitting your own black body radiation. Okay? Now, how do we do this? There are several ways. Lenses, of course, mirrors. Very nice paper written long before you were born, so I really recommend you read it. I thank Jean-François basically for the idea. Yeah, very, very insightful paper. You can also try and actually decrease the emission angle, right? If you decrease the angle towards which you can emit blackbody radiation, you're reducing the blackbody radiation emitted by the cell. And so, as discussed before, you're going to increase your VOC. You can do this with structures like this one, preventing light from going out. This was actually performed onto gallium arsenide solar cells. And you can try and do both things at the same time. At the same time, try and concentrate light, which is coming in, which is to say increase the angles towards which you see the light source, and decrease the angles towards which you're emitting. And this is one of the motivation for many of the nanostructured solar cells devices to claim that you can have built-in behaviors. Now, there is something where I want to warn you here, which is pretty important, is the fact that when you're doing these things, when you're trying to reduce the emission angle, what you're really reducing is just the radiative dark current. You might have many other ways of fluiding your carriers. And when you reduce the radiative losses, you're not changing these other terms, which most of the time are much more important than this one. So you're making a lot of efforts to reduce this guy, which at the end of the day has almost no influence onto the final voltage. So from a theory perspective, if everything was ideal and you only had radiative losses, decreasing J0 from radiation or increasing JSC from illumination would be equivalent. In real life, of course, it's slightly different. Okay? Back to my picture. This here will really be the gimmick for the rest of the presentation, and we'll try and see how the different concepts play here. Okay? So this here was the Suchet quasar limit under one sun. Now if I do the same graph under concentration, what is going to change? Now, what I would suggest you to do here is to try and play the game. So if you can take your phones or or computers or whatever, you go to this website here. Go on, do it. WooClap.com, PVSchool. This here was the graph for Suchet quasar under one sun. I'm going to make the same graph with Suchet quasar under concentration. What is going to change in this graph? Do you think it's this thing which is going to change, that thing, that, this? What is going to be different? For now, we have 2 answers. 3 piling up. WooClap.com/PVSchool. It worked for 34% so far. So let's try and think what is happening. What is happening is I'm either increasing my generation rate or decreasing my local recombination rate, let's say, which means I'm going to have locally more carriers. If I have locally more carriers, it means my Fermi level is going to go up, because I have more carriers. If my Fermi level is going to go up, it means I'm going to be able to collect more work and less heat when I'm getting one of the carriers out. Okay? So let's see the 20 answers which we had so far. Ooh, that's spread. So let's see how it goes. If I go here and I will plot the same thing now under concentration, what changes is this. Okay? It's the same gap. I'm not changing anything to the photons. I'm not absorbing. I'm not changing anything to the relaxation of photons from up here down to the bottom of the band. What I'm changing is I have more carriers, larger Fermi level splitting, more work per carrier, less heat per carrier extracted. So I'm reducing this heat loss. Okay? So this is really what concentration helps you to do. Now, there are issues with concentration. There are things you should be wary of. You go for a higher current density, so you might have resistive issues. You're going to have issues with temperature kicking in at higher concentration and degrading the VOC, because for a fixed number of particles, if you increase temperature, Fermi level will go down. Everything in solar cells is about Fermi levels. You can have degradation issues, of course, and you might have alignment problems. Because if you focus the light and the sun starts moving and you're focusing the light out of the cell, you're basically producing 0. Not going too much here into details, because for the last quarter an hour of this talk, I want to go for the new concepts that I introduced in the first place and try and give you this map, this overview of these ideas. So we are interested in reducing losses which are due to high energy photons. We lose part of this energy because photons relax towards the bottom of the band. We might be interested in gathering the energy of low energy photons, which we just don't absorb if they are below the gap. And we can do this either by playing on photons themselves or by managing carriers, which are photogenerated. Okay? And this table will allow us to see what is the purpose and what is the working mechanisms of new concepts. So here we go. Down conversion aims at addressing high energy photons by managing photons. So what we do is we have a high energy photon going in. We absorb it in a system with many energy levels. And this system will relax by emitting 2 low energy photons. So instead of wasting the excess of energy of this guy, now I'm having 2 carriers which are generated. If I had not this system, I would just have 1 carrier. But the blue photon had enough energy to make 2 carriers. Okay? If I want to gather the same photons, but now playing directly with carriers, what I can do is to say, okay, so this high energy electron which I have here instead of letting it relax towards the bottom of the band, I'm going to use this energy, for instance, with impact ionization, and this energy here, instead of being wasted, will be used to promote an electron from the valence band to the conduction band. Same idea, at the end of the day, for one blue photon coming in, I've got two carriers which are photogenerated, two pairs of carriers. Now, if I want to address low energy photons, okay, yeah, I want to mention here hot carrier solar cells, which I will not fit into this table here because they're so important that I will devote a full slide to them specifically. Upconversion is just the other way around. You aim now at low energy photons, so these photons would normally pass through the gap without being absorbed. What you're going to do is you're going to absorb them in two steps, use them to promote an electron in this optical system to a higher energy state, and when relaxing, this guy will emit a blue photon, which now can be absorbed. So instead of wasting these two photons, I have managed to collect them. And the same idea, but now built in, playing directly with carriers, goes this way. I can have an intermediate band here, and I can promote one carrier with two photons up to the conduction band here. Instead of losing these photons, I have now managed to gather their energy. Okay? These here are really the main ideas behind these 4 or 5 different types of new concepts. Now, as I told you, this is not science fiction. This actually works. And so let's try and play around with this a bit. I will flash through these 4 things, and for each of these 4 things, I will show you how it influences the Suchet quasar limit and what has been done experimentally with just 2 very basic examples. Okay? So that's the plan for the next 10 minutes or so. So, upconversion. We can play the game again. This here is what you had for the Suchet quasar limit. If you do the same graph for an upconverting system, what do you think will be different? What will change this time? So upconversion, remember the previous slide? What is upconversion doing? I can get back here if you want. Upconversion is taking 2 red photons, turning them into a blue photon. So let's see what you say. Hesitations. Is it photons which used to be not absorbed, or photons which used to be thermalizing, or maybe radiative losses? We don't know, just in case. So let's see. Upconversion is doing this, essentially. You had photons which used to be not absorbed. They were red photons at a high band gap, so you're losing them. And now you're turning them into blue photons, so you manage to collect them. Okay? And basically, if you remember what we said about concentration, this red line here tells you how much additional power you can win if you make this idea under concentration. So these here are the typical efficiencies, maximum efficiencies, which you can get. Now, this works in real life. Usually, to make these systems, you use rare earth systems, even though they are also quantum dots or organic systems which can be used. And so these rare earth have these very complicated and intricate energy schemes. And playing with selection rules and being clever, you can make this upconversion, which you're aiming for. What I also find really interesting in this paper, in this figure, which is published in this paper, is that you can make a very, very interesting paper using absolutely crappy figures. I mean, this was made with paint, and yet the paper is fantastic, and I really recommend you reading it. In terms of application, there were attempts made by introducing rare earth materials into TiO2 electron transport layers in perovskites. And the introduction of erbium and ytterbium has increased the efficiency of these cells by increasing the current which was actually generated inside the cell. It happens, because it's perovskites, that at the same time introducing this doping with rare earth increased the lifetime and the degradation rates of perovskites for some reasons. And when I said that when you try something you don't know where it's going to lead, that's also part of the results which I had in mind. You might be trying to implement new concepts onto perovskites, because perovskites is also a good way to get your paper going through, and realize that for some reason it might be the key to a longer lifetime of the material, for reasons you had not thought in the first place. Okay, next one is down conversion. So the other way around, blue photon going in, 2 red photon going out. What do you think? So these times, it's down conversion, which means I have a high energy photon coming in. Okay, we're converging. So, yes, indeed, what is happening here is the fact that these photons here are now being absorbed. There again, to show you some examples, there again with perovskites, you see here 2 different collection efficiencies, let's say roughly. And you see that with blue photons, which are here, the control systems manages to get less electron out than the one where you had this additional content which was added. Now, I want to emphasize here something which is important, which is the fact that it's often very hard to distinguish down conversion from downshifting. What's the difference between these 2 things? Down conversion is you have 1 photon in, 2 photons out. You have not lose energy. Downshifting is you have a blue photon in and you're transforming it into 1 red photon. So you have lost energy. You have wasted the energy of the photon, but instead of wasting it here, you're wasting it into this conversion system. Now, why is it still interesting? It is interesting because blue photons can be tricky to collect. If they are absorbed very close to the surface, they will produce carriers which will die very soon, and you might not be able to collect these carriers, which you see often as the EQE going down at high energy photons if passivation is not good enough. So if you turn this photon into a red photon, the photon can go deeper into the device and be absorbed in layers which will be easier to collect the carrier. And this was also the idea to implement this kind of system into CIGS. So I'm really trying to convince you here that these ideas can be relevant for many different technologies. And you see that this here was the EQE for bare CIGS. And by transforming blue photons into red photons, not even making down conversion, but just making down shifting, you could increase significantly what was collected here for high energy photons. Okay, 2 more to go. Multiple exciton generation. What do you think this time? So multiple exciton is you go in with a blue photon, putting some carrier very, very high in energy, and instead of letting this carrier relax by itself, you use this excess of energy to promote another carrier into the conduction band. Yeah, if you look at the slides, it's too easy. Okay, now it's a little bit more spread again. So what is really happening is quite similar to what happened before, is this idea that instead of wasting energy due to thermalization here, we're using this energy to make carriers which we're going to use for electricity. So we're reducing thermalization losses. Now what is quite interesting here is to see that this red contribution is super high here, which means if you do this thing at low voltage, at low gap, you're going to have significant collection losses, which also means that this thing should really be made specifically under concentration, because concentration will help you take advantage of these losses. Now this here is a very, very interesting topic, and we have here very clear experimental signatures of results producing more than 2 carriers, let's say more than 1 carrier for each photon which gets in. This what you see here with PVSE quantum dots. This here is the, let's say, the external quantum efficiency. You see that it goes here above 100%. What does it mean? It means that for 1 photon which you send at this energy, you can get more than 1 electron out of the system at the end of the day. So you did manage to get more than 1 charge per photon, which is the whole point of these things. Now, multiple exciton generation is usually the inorganic wordings for these kind of things. If you use organic materials, you'll be talking about singlet fission. It's slightly different mechanisms, but the idea is essentially the same. The recent paper, who is looking now on singlet fission, so organic systems, made on tetracene layer just on top of silicon solar cells. So there again, these ideas of making some fine-tuning and to take the best of high-energy photons is interesting also for people working in silicon, and actually made its way to nature. Now, this whole point of multiple exciton generation is, I think, extremely interesting from a scientific perspective, because it also really raised a rumpus. There were strong controversies about whether things were happening or not, whether data were correctly treated or not. And so you had these papers where some groups published papers saying essentially nothing is happening in these nanocrystals, which were thought to be the best possible systems to see multiple exciton. And then there was this paper coming out telling, okay, there is no detectable carrier multiplication in such and such systems. Then came this paper, and I just love the title of this paper. In spite of recent doubts, carrier multiplication does occur in these nanocrystals. And these kind of controversies can, of course, be quite painful for the authors which are involved in there. But as a reader, and a few years back, it's very insightful, because it forces people to really lay down all the arguments and to go back to basics. So it's extremely instructive. When the arguments are sound and when the discussion is good, it really helps you to get into the details of what is happening. And the result of all this is also a paper which came out a few years later to suggest better experimental techniques to really distinguish what can be attributed to multiple excitation generation and what is linked to other effects. So it really, to me, shows how scientific dispute can help improving basic knowledge. Last but not least, intermediate band solar cell. Maybe we're not going to play the game again, because now I'm pretty sure you all see how it goes. We're talking here about red photons. So these photons used to be not absorbed here, and now we are absorbing them because we are having a 2-step absorption. So what is going to happen here is this, essentially. And there is this quite beautiful paper with the 3-5 nanostructures. One of the key issues on these systems is to make sure that this intermediate band is well disconnected from the surrounding lattice, because otherwise you would absorb carrier here and it would be extracted, which means that on the other side you can inject carriers here and they will recombine. So if this thing here is connected to the outer world, what is really happening is that you have just killed the gap of the material. And these two structures here show one structure where the intermediate band is connected to the outer world, and one structure where they managed to cut this band and to make it independent from the outer world. And this you see here on the EQE measurement. For the connected band, the gap goes down to very, very low values, because essentially the gap now is here, what you'd like it to be there. While for the correctly disconnected structure, you have some absorption here, some absorption there, and some absorption, and you really see the gap here, which corresponds to the main structure. So there again, you do have experimental signatures of these things. Now, as I'm slightly running out of time, I would just like to brush this idea, which is, okay, now these things I've been presenting, they've been around for quite some time. Why don't they work already well above Suchet-Quasar limit? There are many reasons for this, and this would require quite some drinks and discussions to go through. But I think one of the ideas is that these concepts are vulnerable to non-idealities. They work very well in an ideal system when you start including non-idealities. And as Jean-François said, you should take these things into account when you think about these systems. You can decrease very quickly the maximum efficiency which you can dream of. It's detailed, for instance, into this paper. But this notion of being vulnerable to non-idealities is not a dead end by itself. PV itself is quite vulnerable to non-idealities, and it took some time until we could get materials with good enough quality to have the performances we have now. So there are really two ideas, two ways to go. You can try and increase the quality of the material to make sure that these non-idealities become as scarce as possible. Or you can try and optimize the resilience of the device, reduce a little bit the efficiency which you can dream of, but make sure that you are more able to face real-world situations. I will show you this here with intermediate band solar cells. This here is the Suchet-Quasar limit. So this is the blue curve we had before, and this is the blue curve for IBSC in the ideal world. Now, there are a few things I can take into account to make this situation more realistic. For instance, I can take into account the fact that this transition here might be non-perfectly radiative. I might have non-radiative recombination. Truth be told, I will have non-radiative recombination, and probably lots of them. If I include these things here, I'm decreasing the efficiency of the IBSC. I can also take into account the fact that this absorption here might not be super wide, because I'm making essentially here intra-band transitions. So I might consider not a full absorption, but just a narrow absorption. And if I do this, efficiency goes down. But the worst is to come. If I now have these two things together, both non-radiative recombination and narrow absorption, the efficiency is decreased so much that the IBSC now is not even able to go above the Suchet-Quasar limit. So if you have narrow absorption and non-radiative recombination, the IBSC is just not able to overcome the Suchet-Quasar limit. What do? We can try and fight these non-idealities, or we can try and add something which will make the system more resilient. And as quite often in physics, when you're looking for good ideas, you can go to Richard Feynman. And Feynman came with the idea of Ratchet. Now, the physics of the Ratchet seems very simple. It's the idea that you have a system which can go one way, but which can't go the other way. It happens that what is really happening behind the thermodynamics, which everybody hates, behind this, is pretty intricate and very, very funny. I'm not going here into too much details, but the idea turning this into there is just to have this configuration of the band here, and you can read it just like you would read for the Ratchet, that electrons would go one way, but have trouble going the other way. Now, just for the Ratchet, this simplistic picture is wrong, but it gives you some kind of idea of what makes the difference. And this kind of Ratchet you can engineer by making, for instance, quantum wells, and we made simulations to show that you can have this ground state, intermediate band, and conduction band with an energy Ratchet, which you see here. Now, if I do the same calculations here with the Ratchet works a little bit better than the IBSC in the ideal case. But now if I include the non-idealities which I had before, you see that the Ratchet remains up here when the IBSC had decreased below the Suchet-Quasar maximum. So introducing this Ratchet is not so much a way to win in terms of efficiency, it's a way to win in resilience of the system. I have 5 more minutes to finish this presentation. If you want to discuss about why this Ratchet makes things better, we can go there. We even could prove it analytically, which was quite funny work. But what I want to finish this conclusion with is discussing way to step even further away from equilibrium. So far, what are the systems we've been considering? Either the single junction systems or the 4 new concepts which I have introduced, they all work in the same idea. The only difference between the material in the dark and the material under illumination is that you have more carriers photogenerated under illumination, which means you have chemical potentials which are different in the dark and under illumination. And the only difference between thermal states at equilibrium and solar cell is the fact that the Fermi levels are different. That's the only difference. We can think of how to drive systems further away from equilibrium, making them more distinct from steady states in the dark than just splitting the Fermi levels. And as you push systems further away from equilibrium, as they will try to relax towards equilibrium, you can use their relaxation to gain work. That's what thermodynamics is always about. So how can we go further away from equilibrium? We can change not only chemical potential, we can also change temperature. And that's the main idea behind hot carrier solar cells, to which I will devote 2 slides afterwards. You can decide that you will work not with thermal distribution, but that you will work with distribution which are even further away from a thermal state, which you can't describe simply with just a chemical potential and a temperature, and you might want to give population actually for each of the value of the semiconductor. This state is further away from equilibrium, which means you can probably get more work out of it. I will not go too much into details, but there are ways of considering that light, which you consider is not bringing just heat, but also bringing work by itself. And I will skip this here. So I will just highlight hot carrier solar cells to finish. The idea for hot carrier solar cell is to try and harvest energy here. So it's to get energy before carriers have recombined towards the bottom of the band, have relaxed towards the bottom of the band. Essentially, if you want to do this, you're going to need 2 ingredients. And so when you talk to people making solar cells, hot carrier solar cells, they will essentially tell you about 2 things. So next time you drink a coffee with someone who makes hot carrier solar cell, you know what to talk about. The first thing is you need an absorber where carriers will remain hot. You need an absorber where you're going to have enough time to get carriers out before they relax to the ambient temperature. There are many ways of doing this, and it really shows experimentally. As you increase laser power here, for instance, you see that the carrier's temperature, which is extracted from the luminescence techniques Laurent has presented before, you can get carriers going up and up and up in temperatures. So you can generate hot carriers indeed. We know how to generate hot carriers. We know how to do this. Of course, perovskites are very interested in this as well, because they are very interested in many things. And it turns out that hot carriers can be also interesting to study some degradation mechanisms or some relaxation processes inside perovskites. So it's not just 3-5 issues, it's also interesting in many other types of materials. The other ingredient which you need for a hot carrier solar cell are selective contacts. You need to extract carriers at a specific energy. You can't satisfy yourself with getting carriers as they come at the bottom of the band. It shows in this expression here, and I think it's quite interesting because it generalizes the usual expression which we've seen before. What you have here is the voltage which is provided by the device. This here is the Fermi level splitting inside the absorber where carriers are hot, and this here is the level at which you are extracting carriers. Now what you see here is that if the hot temperatures are at the same temperature at their environment, so T hot equals T cold, this thing disappears, and all that remains is that the voltage is the Fermi level splitting, which makes sense. It's what we've been discussing the whole time. But now if you say that the temperature inside the absorber is different from the temperature outside the absorber, you need to be a little bit more careful, and you will see that there is this thing here which appears explicitly, which tells you that the voltage you get at the end of the day will depend on the energy at which you're extracting carriers. There again, this we know how to do. We can do this, for instance, with resonant tunneling. So you have in this double barrier system 1 resonant level, and carriers can only be extracted if they have this energy of this resonant level. And an experimental signature for this is negative differential resistance. So as you scan the bias on this structure, you're extracting carriers here, so only few carriers which are there. As you polarize the structure, this level here goes down. You're extracting more and more and more and more and more carriers until the point where this level goes below the bottom of the band, and all of a sudden you don't have carriers which are extracted resonantly anymore. The only carriers which you manage to get are carriers which go above the barriers, and this is what you see here. As you increase polarization, you have more and more and more carriers until the point where the resonant level goes below the bottom of the band, and then all that remains is emission above the barrier. So this we know also what to do. And if you put these two things together, what is really going to happen at the end of the day is something which is way more dramatic than what we've seen before, and it's this. It's the fact that we have completely killed all thermalization here. We have made this yellow line disappear, and instead we have this kind of behavior. And you see that here we can dream and go up to the maximum full concentration efficiency which Jean-François introduced before. So I'm going to stop here and leave you with the take-home messages. I don't know if I have made thermodynamic friendly, but I hope you get to see that thermodynamic and electrical engineering are really saying the same thing with two different wording. They are the two sides of the same coin. And it really shows into this equation, which is at the same time utterly simple and really wonderful and very elegant. I think the Shockley quasar limit and how you can try and tweak these different things should now be quite clear, especially there again with the very clear introduction on the matter that Uwe had made at the beginning of the week. Now you get to know all these usual suspects and how they work, what they aim at, and what we can do with them already. And I hope that I have convinced you that even though these techniques will not make it to market in the next 5 years, there is a lot of exciting science to be done in there. Thank you very much.
We'll take one or two quick questions, and then we'll take coffee.
And I have a question for you in the meantime. You can vote for your favorite new concept. Yes?
I wanted to know how you presented the new concept separately, but which one you can combine and which one you cannot combine?
So essentially, I'll let you vote on this in the meantime. Essentially, what you would be interested in combining are things which will aim for getting the best of high-energy photon and getting the best of low-energy photons. Okay? The paper I have mentioned before, this one, for instance, tried to combine photon conversion together with multiple excitation at the same time. So exactly what you're having in mind, combining them. And what they say here is, if you make 100% efficiency upconversion system, and on top of that you have multiple exciton generation at a good efficiency, you get very good efficiency. And now if any of these starts degrading with respect to this ideal case, you're going to get a maximum efficiency which is much lower. So you might want to combine these things because they aim at different goals. But on the other hand, it might make your system more vulnerable.
Meanwhile, you can still vote. So thank you. It's very nice talk. I think I understood some of the topic now. So this is very nice as compared to the multi-junction stuff. It's a very small marginal gain. It's a lot of work to get a small marginal gain, and here you offer perspective for a large, so disruptive, so a large gain is maybe a simpler, one stuff you do instead of having a lot of small stuff to get in. So there is a lot of material science,
yep.
And it's a fantastic research topic. Now, the other side of the problems with the multi-junction is what I mentioned at the end, is that you change the spectrum, you change the temperature. It's not
yep.
so resilient, especially if you go to the series connector. If you go to the 100 wires for 100 solar cells, that might work, but it's another problem. Now, can you say something about the resilience of the different concepts, or some of the concepts that you would know, against, say, if I change the spectrum, if I change the temperature of the outside world, does it still work or collapse as with the series connected multi-junction sometimes?
So short answer is I don't think I can answer this question properly. So I will still try and say something, but I don't have a very clear answer on, for instance, which of these concepts would be more robust against temperature change or spectral change. There is one thing I think, and I think Uwe highlighted it before, is the fact that we're looking for the maximum efficiency point, which should be somewhere around here, but this thing is quite flat, on the other hand. So I wonder, up to some sense, if you change spectrum a little bit, if you change temperature a little bit, it might be that the actual optimum point would move from here to there. But I wonder if the difference between the values which you get is going to be very different. It will depend on how flat this curve is. Now, of course, you see here that it's less flat than before, which tends to say it is probably more vulnerable to any change. You would have to adjust band gap differently. But there again, I've not dived into this so far yet.
Maybe you can vote on WooClap.
What I know is that I've made calculations recently for a solar cell on Dune. I don't know if you know Dune, the book by Frank Herbert. I've calculated how much solar power you could get if you were on Dune, and you can look at using the light from Canopus, which happens to be 170 times larger than the sun and about 1.5 times hotter. And it was very disappointing to see that silicon was once again probably the best material for this.
But we are on Earth.
Okay, there's just 21 votes here out of 46%, but so if you want to vote, it's now. And the winner is hot carriers, yay!
Thank you very much, Daniel.